So when we're solving log and exponential equations, there's really two different things that can happen. You can start with a log equation or you can start with an exponential equation, obviously, right? But what you want to have happen is you want the one side of the equation to say the same exact thing as the other side of the equation. So in its most basic form, in the easiest form of these types of equations that you can see, you could see something like this. Now this is really, really, really nice if the equation looks like this, because in order for these two equations to be equal to each other, what does x have to equal here? It has to be 5, right? Because the left side of the equation has to say the exact same thing as the right side of the equation, which is great. The only issue is when those bases aren't the same. Now it doesn't matter what is going on with the exponents at all. I could have a grand equation. I could have a huge equation going on like this. If I ask you to solve for x, if the two bases are the same, then life goes on and everything is good. Because all we need to do is drop the two logs because everything else has to be equal and solve it. Not logs, exponents. And I would just have to solve this equation and everything would be great, right? Because that's like a 3-step algebra problem, which is no big deal. The issue comes when we don't have the same log base or we don't have the same exponential base. If we don't have the same basis, we have to try something in order to help us solve these equations, all right? So what this means is if I'm asked to solve an equation or if I'm asked to try and figure out how to solve one of these without the same basis, I have to go through and find ways to fix it, okay? So what that means is if I have something that looks like 3 to the x minus 1 equals 9 to the 2x plus 5. If I have an equation that looks like this creates an issue. Because the only thing that I have, or the only idea that I have with this, is that I can drop the bases. But these bases are not the same, so I can't do anything to that. So what a lot of people are going to try to do is they're going to say, well, you know what we can do? We can just multiply that left 3 by 3, and we can call it 9. But then we've unbalanced the equation, right? Because if I only multiply the left side by something, and I don't do anything to the right side, I've unbalanced the equation now, and it's not the same equation that it was before. So the only thing that I can do, and this is the biggest hint that you can have, is to rewrite. You need to rewrite something. I don't care what you rewrite, but you need to rewrite something in the equation so that the new equation has to be the same or has to be equal to the first. Your new equation has to be equal or the same or balanced with the first one, because if it's not, you're not going to get the right answer. So what that means is I can't just rewrite something, because again, the next thing that people are going to want to do is they're going to want to say, well, I could just do 3 squared raised to the x minus 1 equals 9 to the 2x plus 5. They look at it like this, and now all of a sudden that equation is no longer equal, because 3 squared is the same thing as 9. So if you call it 9 to the x minus 1 equals 2x plus 5, so this would end up being 9 to the x minus 1 equals 9 to the 2x plus 5. Are these two equations equal to each other? They're not. I've literally just looked at that first equation and said, nah, I don't like it. Let me change the number and call it good. That's what I did, right? And if you do that, you're going to end up with an incorrect answer. So what you have to do is you have to find a way to rewrite the first equation, so that way the first equation is equal or equivalent to the second equation. Go ahead.
Could you just square the second equation so it was 3 equals and then just add?
That's absolutely what I would do. So what Sean is saying is, should I just take 3x minus 1 equals 3 squared to the 2x plus 5? And now if you look at this, I have not changed anything between the first equation and the second equation, right? So let me write this or circle this and put a big red X through it, because this is not the right way to do it. But if you look at this one, are this equation down here and this equation up here, are those equations equal to each other? Technically they are, right? Because it says 3 to the x minus 1, okay, that checks out, same exact thing. 3 squared is 9 to the 2x plus 5, 2x plus 5. Every single thing about this is the exact same, except it looks a little bit different, okay? So now that being said, I am going to distribute this through, because when you raise a power to a power, you multiply. So I'm going to be left with 3x minus 1 equals 3 to the 2x or 4x plus 10. So I get 3 to the x minus 1 equals 3 to the 4x plus 10. And now we have it back to that beautiful thing at the very beginning when I said that I could just get rid of those at bases. Now you have a base equal to a base. That's great. Everything is perfect. We just drop those and we solve the equation. So now it's going to be x minus 1 equals 4x plus 10. Because in order for those to be the same, the exponents have to be the same. So now I can solve. So I'm going to add 10 to both sides and get 9 equals 3x. So that I'm going to get x equals 3. Is that not right?
Wait, are you subtracting the 10?
Sorry. Got ahead of myself. So it's going to be minus 11 equals 3x. So then divide by 3, so I get x equals negative 11 thirds. That number seems better. All right, and that's how you would solve for x with these equations. Now, it's really, really nice when they work out super nice like this, right? When the power can be rewritten as a power, or the base can be rewritten as something else where the bases can actually end up being the same. Every once in a while, that doesn't happen, okay? So every once in a while, that's something that we're not going to be able to solve. So what I'm going to do instead is I'm going to show you what happens when these things aren't the exact same. So let's start out with a really, really basic one where we have like 2 to the x equals 7. Now these bases are not the same, right? Obviously 2 and 7 are not the same, so we can't just drop them, right? We can't just get rid of them. Is it possible for me to rewrite 7 as 2 to some power? I can write 2 to some power equals 7. What is 2 to the what power equals 7? It's going to be tough, right? It's going to be really tough to rewrite 2 to the some power equals 7. Now, is it possible? Maybe. Who knows? But in all honesty, the only way you're going to figure out 2 to the what power equals 7 is by using logs anyway. Because if you realize this is what this question is actually asking us. It's saying 2 to the what power equals 7, right? Which is the same exact question as what I'm saying 2 to the what power equals 7 for here. So the way that you're going to solve this is by using logs. The same exact way that you solve this using inverses, you're going to solve it using logs. I have 2 to the x power. I want x to be out of there. If I want x to be out of there, how do I get rid of an exponent? I take the log of it. When I'm taking the log, I use the same base as the base that I have right now. So what I'm going to do is put a big log 2 on both sides. So I'm taking log base 2 of both sides. And then everything else goes into the problem the same exact way that it was before. And then as we learned with logs, when I take log base 2 of itself, it goes away. So this number, or that expression right there will cancel. And it will leave me with x equals log base 2 of 7. Now something really, really important that you need to remember from Monday, or whenever it was the last time we talked about this. This is when I taught you the change of base formula. This thing right here is a number. That is a number in your calculator. Your calculator will give you that number. It will tell you what the number is. Okay? You can do this 2 ways. One, you can use the log base formula thing in your calculator by hitting math and then scrolling down a whole bunch of times until you find the word log base. If you don't find the word log base, then the way that I'm going to solve this in my calculator is log 7 divided by log 2. So log 7 divided by log 2, I would imagine it's 2 point something. Does anyone have the actual number? 2.8. So around 2.8, and that is our answer for x. Okay, now these ones you're not going to be exact on because you can't. You can't really be exact on it. It's an approximation. It's a number that goes on forever. If you wanted to be exact with it, then your exact answer would be this. So it's the thing circled in blue that is the exact answer. The approximation is 2.8. Okay, make sense so far? Everybody okay so far? All right. So that is how you solve for exponential equations. Okay, it really isn't that bad if you understand how to solve for inverses, then you really understand solving log equations. All right. So when you're dealing with logs, it's the exact same concept. If I have something like log base 2 of x equals log base 2 of 3x plus 5, the same exact thing is true that it was before. So if I have a base and a base that are the same, in order for these two things to be equal, then that means that this thing and this thing have to be equal to each other, right? In order for them to be equal to each other, then that means those two red circles have to be equal to each other. So in order for those two red circles to be equal to each other, all I have to do is drop the log on both sides, and then I end up with x equals 3x plus 5, and I solve. So I subtract 3x from both sides, so I get negative 2x equals 5. So x equals negative 5 over 2, or 2.5 if we're going to call it that. Logs happen the exact same way. Everything about this is the exact same, except instead of dealing with exponents, you're dealing with logs. But the properties between these two things are identical to each other. You're either going to get the bases to be the same, which, spoiler alert, getting the bases in a log doesn't happen. Okay, so like if the two bases are not the same in the log, you can't do this anyway. Okay, you know I just gave you a question where it was like 2 equals, or 2 to the x equals 8 to the x minus 1, and we could change these bases. You know how we could just do that? You are not going to be able to do that here. So this one you cannot change. This is unsolvable. I don't know if that's a word. Is unsolvable a word? Okay. You can't change the bases here. All right. So on the one on the left, you can change the bases for, because we know those properties of exponents. The one on the right, you cannot change the bases. If the logs do not match up, you cannot change them. Make sense? Yes.
Couldn't you just like get out the logs, like put 2 in front of both and divide by 2, and it would just be a really complex equation on one side?
Kind of, you could, but we aren't going to get to the math that would allow you to solve that. So so when I say it's unsolvable, I mean it's unsolvable for us in this class. There is a way that you could actually solve this, but that is not a math that we are going to get into because it's not something that we're ever going to have to use. Okay. So the only other type of equation that you could see, or the only other thing that you could see if you were trying to solve something like this, is if I have an equation like, I'll leave you with this one, or we'll try this one, because this is going to take the exact same kind of steps that we took last week. So this is going to take the same exact kind of steps or ideas as what we just talked about using logs and exponents on Monday with condensing and expanding. What we want to do is we first want to isolate the log. You want to get the log by itself, which means I have 2 logs there. I could either subtract 1 log from the other side, but I still don't have 2 logs, because if I subtract log from this side, I'm going to end up with 2 minus this, and I can't drop those off. So what you need to do first is you need to condense. So first things first, I'm going to leave you with this tonight so that you can try it, and then we'll come back tomorrow and we'll play some Luke it over this stuff. But the first thing you're going to do is condense it. After you condense it, you are going to have to exponentiate. So I'm going to see if you can fight your way through this one and see if you can solve it. And if you can, that's great. If you can't, then we'll work through it a little bit more tomorrow. Okay? Any questions you guys have?